We'll go ahead with the continuation of this conversation. On these kind of problems, here's the big thing I'm seeing. You can all do the math. Every single one of you is perfectly capable of doing the math. It isn't hard. And I will speak for myself as somebody who breezed through Calc 1 and 2 in college and barely got a C in college physics. It's not the math. It's applying the math. Because physics is a year of word problems. This is math applied to the real world. Have I told you my engineer, physicist, and mathematician joke lately? What's the difference between a physicist, an engineer, and a mathematician? An engineer assumes that the equation is an approximation of the real world. A physicist assumes that the real world is an approximation of the equation. A mathematician has yet to understand that there's any connection. This is applied math. So what I'm seeing with headings on sum of forces and vectors, on the homework specifically, when I passed it back, I'm really impressed that many of you can read and you can actually copy exact words down from the answers. That's wonderful. So people wrote things like, 96 degrees counterclockwise of the positive x-axis. Yep, that's what the book says. Do you understand where that heading is? And for those of you who some of you didn't have any drawing that would indicate where that direction was, but you had the exact words from the key. That concerns me because I then start to think, do they actually know where that heading is? On a test, can they find the heading for themselves? You can get an angle, but where is that angle? That's the big question. So once you've gotten on something like this, or even a simpler sum of forces problem, once you've gotten the sum of forces on each axis, and I'm making up numbers here because of course I didn't have any magnitudes here. So let's say this is 14.5 newtons up, and this one is 7.3 newtons right. Once I have the sum of force on each axis, this is where this is exactly one of those nightmare multiple non-perpendicular vectors problems. I do this for myself. And now I have something that I can use a resultant with, and I can see, oh, well, that's to the right from straight up. Or I could say, oh, well, that's this many degrees above the horizon to the right. But I have to have that piece, or I get a number, because I had a lot of people say, well, I think I reversed my opposite and adjacent. Well, right, because you didn't do this. And if you don't do this, you don't know which is opposite and adjacent. You know you have two numbers. You know it's inverse tangent of one over the other. But unless you can actually see where that resultant is, you don't really understand where the numbers go. And that makes it much harder to describe that angle. Does that make sense? So make sure that you put those final pieces together. Okay, what are the other things I was seeing? So we're going to do two things. We are going to do some force attention problems, and we're actually going to get out, I have a little object here in this room called a parallelogram board, and we're actually going to create some physical force attention problems. And then, of course, as we go, we're going to do force attention problems with two of our dear classmates, since they'll be flying during the week leading up to the play. I think we're going to go to the auditorium on a field trip, and we're going to watch people fly while we do force of tension problems involving their flight. Won't that be fun, kids? I knew you'd love it. Okay, so I've got a picture of the little mass hanging on the force of tension board, and this is one of the simple force of tension problems. There's my mass. There is my force of tension. There is my force of gravity. I wish I could edit that board out of there. Let me make those easier to see. There. Is that better? So there's the center of my object. The forces are originating out of the center of my object, or at least that's how I represent them, the center of mass, in my free body diagram. This is really easy because we know there are no forces on the x and y axis. Sum of forces on the x and y equals 0, and there are literally no forces on the x. None. But the sum of forces on the y is also equal to 0, though there certainly are forces on the y-axis. What are they? Yeah, okay, so we can start that way with all the forces up minus all the forces down. And we know that, and I'm going to go ahead at this point and set those equal. So 0 equals, well, what forces up do I have? Force of tension. What forces down do I have? Force of gravity, which is equal to mass gravity. So we know that force of tension and force of gravity are equal in magnitude. Well, that's easy. You can all do those. It's just hanging there. Let's make it more complicated. Okay, so I've taken pictures of this thing at 3 different points. And in the first point, I will mention that this line there is really completely slack. There's no tension on it. Have you heard the term like taking up, making a line, leaving a line slack versus having tension on a line? That's what we're talking about here, is tension in a line or a cable. So in that first one, there's no tension on this. All the force of tension is still on that cable, or that string. It's actually pulley cord. Well, when I come down here, I've changed that situation a bit. I have a force of tension in each of these. They're not equal, and this is actually a lot like the problem with the mastiff. There's a 90-degree angle between those two cables. Now, I don't know what the angle with the ceiling or with the vertical is, but could we figure out the force of tension in that? Yeah, of course we can. In the last image, and I think I got it pretty close, I think these are about equal. So we would draw the force of tension as originating, and of course this is an approximation of the real world. Force of tension is originating out of the center of that object. We would need to know this angle. And with that, and the force of gravity as knowns, we can compute the force of tension in either one of those cables. As this thing moves, and there's no way for me to take a picture of this moving, but if you just take a look at it happening right here live, as this thing moves, the force of tension at every single point in this thing's travel, the force of tension in each cable changes, because one cable takes up more or less tension as we share that load unevenly. When we get out to here, look at that. The force is almost entirely on the x-axis. We've got very little force on the y-axis on the cables. Now, is there force on the y? Yeah, of course there is, because there's still gravity, but we're transferring that force very oddly. So the further down we drop it, we see that force of tension shift. Okay, so let's do some actual numbers on one of these. So I've got a 43 kilogram object hung on 2 cables, which are making a 50 degree with the vertical. Be careful where your angle is. Okay, so in this case, I'm going to start, as I typically do, with a sum of forces on the x. This thing is holding still, not moving side to side, not moving up and down. Force of tension on the x is equal to 0. Sum of forces on the x is equal to 0. Sum of forces on the x is also equal to what? All the forces right minus all the forces to the left. So if we call this FT1 and this FT2, I'm going to go ahead and draw out that. Well, I have force of tension X1, force of tension Y1. And why am I putting my x and my y for its tensions there? Okay, you just looked at me like I had 3 heads. What did I screw up?
Me?
Yeah.
I just did my triangle
on the inside. Okay, and you can do that. Well, let's talk about that. Excellent. Excellent. Thanks. So because we were told that this angle is 50, do we have to do the x and y out there? No, we don't. I just like to dummy proof myself as much as possible because I tend to make really stupid mistakes. So what I know is that if this is 50, this angle here has to be what? 40. So can I do my x and my y in there? Of course I can, but I have to take the complement. So as long as I can keep track of that, fantastic. You can do either one. You can certainly do either one. Yeah. I tend to try to use as much as possible the angle that's given because I'm less likely to screw things up. And if I use the angle that's given here, that puts my triangles down on the outside. So you can do either. Okay. Force of tension x, well, I guess x2 is to the right, huh? Minus force of tension x1 equals 0, which just tells me that those are equal in magnitude. So force of tension x2 equals force of tension x1. Okay. Why am I doing this? Why is this useful? As long as those angles are equal, what we're doing is basically a geometric proof that says that the forces of tension are going to be equal. So if I look at my little triangle here, and this is my angle, FTX is opposite my angle. So FTX equals force of tension times sine theta. So I can write an expression, FT2 sine theta 2 equals FT1 sine theta 1. I know that if theta 1 equals theta 2, therefore, sine theta 1 equals sine theta 2. So I can get rid of those. And I've just proved to myself, I've laid out the proof that the force of tension is equal in each cable. Okay, so we've proved to ourselves and anybody else who cares that the forces of tension are equal. Well, now let's get to the juicy axis. And we're going to do sum of forces. I'm going to get rid of this. Sum of forces on the y. Well, it's 0 because it's not moving. But sum of forces on the y is also equal to all the forces up minus all the forces down. As these situations get increasingly complex, the big thing you have to make sure of is that you're identifying all of the forces up or down, because we will start adding forces. Right now we're doing, really usually 4 forces, 2 in each direction, maybe an occasional split force. But as we go, we will add forces to the situation. So you got to make sure you're accounting for everything. So what forces up do we have? We know that these are now equal. So force up equals force down in magnitude. What forces up do we have? Well, force of tension y1 plus force of tension y2 together have to equal force of gravity, which I didn't even put on my free body yet. There. Based on the work we did here, if we look at this 50-degree angle, force of tension on the y is adjacent to that angle. So FT1 cosine theta 1 would be force of tension Y1. FT2 cosine theta 2 would be force of tension 2, and that's all equal to Fg. And at any point here, we can trade that out for mass times gravity. So, based on what we proved up here and over here, that force of tension 1 and 2 are equal, and that sine theta 1, sine theta 2 are equal, we can actually substitute Ft1 cosine theta 1. And I wanted to bring up, and I don't remember who did this. Somebody did this on the homework or the quiz. There are two ways to crack this egg. So if I give you x plus x and ask you to express that without using addition, you would all say 2x. Okay. You can do the same thing here. And you can say that this is 2 Ft1 cosine theta 1 equals mass gravity. You can also factor out your Ft. It doesn't matter. So you can also say Ft times cosine theta 1 plus cosine theta 1 equals mg. Now if you do that, guess what? You can still then make that into 2 cosine theta 1. They're mathematically the same. Getting used to doing some factoring in these is probably not a bad idea, because we get to ones where you have to factor to solve. Very often we'll get presented with some later on where you don't get mass, and when you start out looking at it, you're going, I can't solve this. Mass isn't given. But there will come a point where you can magically make mass disappear by factoring it out. So it's not a bad habit to get into. Okay, so from here, of course, I think any of you can pretty easily solve this for Ft1. So Ft1 equals mass gravity divided by 2 times cosine theta 1. And that's pretty standard for the force of tension problems at an angle that we get. These are as long as the angles are equal. If the angles are not equal, like in number 5, the horrible mastiff problem, we have to know the ratio of the, if we don't start off knowing the angles, we have to at least know the ratio of the angles or the ratio of the forces, because that gives us sort of a little toehold where we can get in and start the problem. Okay. Okay, so these are the two issues that have been identified on force of tension. Let's do a quick little simulation here. Well, no, that gives it all away, doesn't it? If I am told that there is a 32.5 degree angle with the vertical, where's my angle? Is it here or is it here?
I think I have trouble. I always want to draw like right up the middle. Like,
oh, okay, but remember that,
right there.
yeah, and you can do that, but first you got to figure out where the cables are.
Yeah.
And this is that whole physics is the actual world versus just pure math, which isn't. So let's practice taking the angle from the end of the cable into the center.
Okay.
That's a good one. Oh, duh. And exactly what you wanted to do with drawing. Okay, so 32 with the vertical, first of all. Where is this 32? The cables make a 32 degree angle with the vertical. Wall or ceiling? Wall. The vertical is the wall. A room with horizontal walls is a very strange idea for us. Okay, so this is a 32.5 degree angle with the vertical. Now, if you prefer to draw your triangle in here, That's easy because guess what? That is the same as that. Okay, that's just some geometry. So you can translate, is it translate? My math language I think might be wrong. I'll go ask Mr. Andres later. You can move that angle in because we know that, you know, within this sort of rectangle that's formed here, that angle is going to be equal to that angle. Okay, so then if you feel more comfortable with that, if we're using this angle, I'm looking at my y, is that opposite or adjacent? It's opposite. And my x is opposite. Good Lord, Moser. My y is adjacent. So drawing yourself, identifying where the angle is and using the correct trig function are largely related to drawing a good picture. Draw a big picture, draw a good picture, leave yourself lots of room. If you want to grab colored pencils and color code your, sub portions of a force, do it. Especially if you're a visual learner, that's a huge help. That's why I like this, because I can color code my x and y components of each force, and I'm a visual learner. Does that help with both of those? So we'll stop this video and we'll move on to doing sloped surface problems.